if your metal is octahedral. Wow, it's going to be one of them days. If your metal is tetrahedral, you get to be chiral if you have 4 different groups around that tetrahedron. And in coordination complexes, that is unlikely to be the case because the ligands that go around this, a lot of the time that we're seeing them are part of the solvent system. These are waters or they're ammonias. So we probably don't see anything tetrahedral that is of importance and being an isomer of one or the other. Unless, like, we know things like this happens. If we saw this on Tuesday, that's tetrahedral. So it is possible, it is plausible that you could put one of these be a chloride, one be a fluoride, one be an iodide, and whatever one I've missed, chloride, bromide, iodide, fluoride, right? And make 4 things. But that's going to take a little bit of effort. We're probably not going to see isomeric coordination compounds for complexes for the tetrahedral geometry. Okay. What we will see when it goes square planar. Tetrahedral is probably not going to be something that we need to look at. Square planar is a thing. Nickel makes lots of square planar complexes, and it is feasible that we make this ligand here be A, and that ligand there be B, and then I would have these 2 possible isomers. This is cis, and this is trans. In fact, I should look this up because it's just brought a thought to mind, and I don't have the exact molecule in my head. I'll have to look this up. Actually, I can even turn this on. There is a little molecule called cisplatin. There it is. Platinum, palladium, and nickel all in the same group on the periodic table, all D8. This on the left And the one on the right is called transplatin. Cisplatin is used in chemotherapy. Transplatin is not. Transplatin does not have any kind of drug activity that we have so far discovered. But cisplatin is a fairly effective, although now, in terms of what people are used to nowadays, a bit harsh in terms of chemotherapy, but that's an anti-cancer drug. It says right here. It says right here. Well, obviously, if one of them, there's only 4 places. So if one of these is cis, then the other 2 are cis as well. Okay. There's more. A little bit more. Chelating ligands can only be cis. They can never be trans. Okay, let's see if I can remake cisplatin. Okay, so we know that cisplatin has some anti-cancer efficacy. Let's go ahead and just do some science. Just tinker with it and see, oh, wonder what happens to its toxicity versus its efficacy if I change it just a little bit. Is it the chlorines that are making this anti-cancer? Is it the platinum that's making it anti-cancer? Is it the cis part? Is it the amines? But what if I took those 2 amines and instead of them being individual monodentate amines, I changed them to be a bidentate ligand? Okay. Do that. My bidentate ligand that I could start with would be this one. What did we call that one? That was ethylene diamine. It's not its real name, but it's kind of stuck. These things, they go into the books, they go into use, and if they go in early enough and they get used enough, then the name sticks. So this is N. Well, can you see this? That distance right there? And this almost geometry right here. There is no way that you can make that go all the way across from here to here. You just don't have it. It's always going to be this way.
Wait, what is that for you? Why is that again?
There's just not enough distance. This is too far. This, if I could measure the distance between the black dot, the red dot, and the blue dot, the distance between the black dot and the blue dot is significantly less than the black dot and the red dot. And so the little ligand just can't stretch. It just can't stretch that way. Plus, well, it's not really a factor, but if I make this chain longer and longer and longer, there's a little bit of organic chemistry in here. If I, instead of making this ethylene diamine, I made it diaminopropane, because ethylene diamine really should be diaminoethane. Would this still work? Look at this. What shape is that? It's a pentagon. Are pentagons stable in nature? Yeah. Nature's full of pentagons. What about if I make the chain a little bit longer? How about now? What have I got now?
7, 6. 1, 2.
It's a hexagon. Do we see hexagons in nature? Yeah, all the time. So that one's good. Now, what about now? Not so good. Heptagons, octagons, nonagons, decagons, not so good. So we could make this. And if I replaced the two individual amine ligands with one ethylene diamine, I don't get the trans isomer. I don't. I'm now locked in to the cis isomer because my my ligand cannot reach. All right, what about if I put two? I'm gonna have to name that. What if I put 2 in? It's a platinum. Oh, okay. So the chlorides were doing something that I've now, because now from going from here to there, I've replaced both of these chlorides with another ethylene diamine. And now I have to do something that I didn't do here. Chloride is chlorido, it's negative. That platinum is platinum 2+. Everything in the nickel, platinum, palladium group, group 18, no, sorry, group 10, is D8, 2+. 2+ is my dominant oxidation state now. So what I need for this, that goes back to being an obvious complex ion. This has the charge balancing ligand built in. Okay, let's do some naming. When you name an ionic material, you name the metal first, cation first, and then the anion. When you name a complex ion, we do the same thing. We would name the metal cation first, and then we name the ligand, and then, if we know it, we name the anion. Probably 2 chlorides, because I just displaced them. Probably 2 chlorides. We would name them last. So we've always named metal cation, non-metal anion. Now we name metal cation, ligands in the middle. Then, if we know it, sometimes we don't even know what this is. Okay, so this would be platinum And then I have 2 chlorides. So dichlorido, ethylene diamine, and that platinum is in platinum 2. You could write the 2 in. If you didn't write the 2 in, we would have to figure it out because there's no charge. So be polite and write it in. And go through the ligands alphabetically. So chlorido is before ethylene diamine. Okay. This gets to be platinum. And now I have 2 ethylene diamines. How do we say that?
Maybe diamine.
It would be diethylene diamine. Or at least you'd think so. It's not. We use slightly different naming systems. And at first think, why are they doing this? But they're actually telling the reader something because you might not know what ethylene diamine is. And I'm going to give you a clue that it's special and more special than chlorides in a minute. Okay. For monodentate ligands, you have 1, it's mono. I probably don't mention it. 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa. We are going to see things that go hepta and octa. We might even see things go higher than that, but not normal stuff. So this is where octahedra ends, right? So we probably really only need to go up to 6. If you are chelating, so if there's only one of them, we never say mono, right? We might. In the case of like, you take hexaqua cobalt 2 and you just change one of the ligands from being a water to an amine, you might say pentaqua monamine. So the 1 for chelating is monokiss. But we're probably not going to use it. The same way that we don't tell things that there's 1. The same way that when we write a chemical reaction, if the coefficient of your reagent is 1, we don't write it down. C plus O2 makes CO2. I don't write 1C plus 1 O2 makes 1 CO2. We just don't do it. 2 doesn't get to be di. It doesn't get to be bi. It gets to be bis. And 3 gets to be tris. And 4 gets to be tetrakis. We're probably not going to see more than that. Because once you're at tris, if you're chelating, if you're bidentate, 3 bidentate ligands is a coordination sphere of 6. That's octahedral. That's probably where we're going to cap our investigation into coordination chemistry. So we're done. We're done. It's these two. These are the two that are in common usage, okay? So what's the name of my new little complex ion right here?
Platinum, bis.
Platinum. Bis.
Not bis, it's bis ethyl diamine.
Ethylene diamine.
And then GT. Is it something to do with the chlorine? If you could do with those.
Now, these go back to just being chlorides.
Okay.
They're not ligands anymore. They're not attached to the metal. They're just balancing the charge. So do I have to say dichloride? Can I just say chloride? Yeah. How about you tell me what the oxidation state of the metal is?
Oh.
Platinum, bis, ethylene diamine chloride. That tells me everything that's inside the square brackets. It tells me the oxidation state of the metal. And then it tells me everything that's outside the square brackets as well. And I have enough high school chemistry to know the chlorides are 1-, and therefore I'm going to have 2 of them to balance this charge. All right, let's look at some octahedra. Now we do have other geometries than square planar, tetrahedral, and octahedral. And in fact, I mentioned it very, very briefly, but if you take an octahedron and you twist it just a little bit, you make a trigonal prism. And what we're going to see with the chelating ligands is they might twist the geometry to be irregular from octahedral and become more of a trigonal prism. Let's see if we can spot it. I'm not sure that I've got it, but we'll see. So in the 6-coordinate world, let's look at some octahedra. All right, if I have a central metal ion that is surrounded by 6 ligands and they're all the same as each other, there clearly is too much symmetry in that molecule for there to be any kind of geometric isomer, right? Because all of these are the same as each other and I just have to move it around a bit and I get itself back. What if I change that ligand to something else? Does this generate any geometric isomers? Because what we're looking at now is geometric isomers. Cis and trans. It's geometric isomers we saw it in organic chemistry. Does that generate any geometric isomers right here? No. What happens when I add a second one? Think harder. Those two complex ions have exactly the same chemical formula. Are they the same molecules as each other? No, they're not. This is cis, and this is trans. So we could have something as nice and simple as that. Versus this. They are different from one another. What's the name of this one here on the left? I'll let you catch it. Name of the one on the left.
So, cobalt,
Yeah.
then when you name the NH3 unit?
So you'll name them. Which one comes lowest in the alphabet?
Yeah,
What is that?
or,
With a W? And what is this?
So it'd be,
This is amine with two M's. Okay, this is tricky because the people who named nitrogen stuff didn't get that act straight. We've already seen in organic that there's two completely different molecules named amide. NH2 minus is called amide, and then that big carboxylic acid derivative is also called amide. That's not good. The neutral, meaning uncharged, but basic RNH2 is called an amine, A-M-I-N-E. This ligand, listen very carefully, is amine. Amine, amine. There's an ever so slightly different emphasis on that first syllable. Amine. Amine. That's an amine. 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 Ever so slightly different. So, lower in the alphabet than that. Let's go.
it's not, no, it's dye.
Yes, because these are monodentate ligands. So this is cobalt, di, amine.
Is it exactly?
It was
No,
right
wait,
there.
there's four. Tetra. Tetra.
So this would then be tetra aqua. Condense that to tetraqua. But we don't want tetra aqua. Okay. And then people look at that with two A's together and think, do I pronounce that the same way that I pronounce aardvark? Tetraqua. This is cobalt 2. And then we don't know what the counter ion is. we could say, look, that's a sulfate. The sulfate's outside the brackets, and therefore there would be a space. The only time covalent molecules don't have spaces in them, ionic molecules do. This is ionic. And the space comes between the positive part and the negative part. Everything inside the bracket is positive. So all of this is one word. And then a space. And then sulfate.
Do we have to write cis?
Yes. And when you write cis, I know I write in all caps all the time. When you write cis, it's lowercase and italicized. If you cannot write italicized, because it's the 1950s and your typewriter doesn't have italics, you underline the word cis or trans. Let's make that ethylene diamine into a slightly more interesting ligand. Where's my eraser? If I use a bidentate ligand, I cannot make that bidentate ligand stretch across the metal. Can you see that? That could not possibly happen. The other stuff's in the way, right? So I can only get cis geometry out of a bidentate ligand. So if I have just the one bidentate ligand, I only have the cis isomer. What happens if I have two? Let's think. Let's go with copper. Can I do copper? What about manganese? With manganese. DPPE is diphenylphosphenoethane. It is a bidentate ligand with an ethane bridge and two phosphoruses. It looks like this. Those phenyls, those are C6H5 rings with two diphos, as it's known, ligands. I have the possibility of two isomeric structures. This one. And then
What was the name of the molecule we made organic that we had to use that
did the Wittig reaction, and that has a phosphorus in it, because phosphorus is an oxygen scavenger. This one is quite stable to where it does pick up oxygen, but not really badly. The deal is those phenols want to keep the other stuff away from it, and it slows down the way that this reacts. That's my one isomer. Can you see what the other isomer is? Oh, I didn't write the H.
What?
When things get complicated, what you do, like on the organic test a little while ago, I wrote, show me all the isomers for C6 Br4H2. Okay. And the trick is, stop thinking about the bromines as being substituents to that ring, and now think about the hydrogens as being substituents as the ring, and they can only be ortho, meta, or para to each other. Don't think about the bromines, don't think about the big stuff. Look at what the relationship between the other thing is. So those diphosphors here, oh, big, ugly, you have to look at them. Well, if you look at the waters, what are the waters doing?
Chilling.
The what?
Chilling?
Yeah.
Chilling it out?
And what would their geometry be
Um,
to each other? What's their relationship to each other?
far apart. What does it mean?
Yeah, and what's the word for far apart on the opposite sides of the molecule to each other?
Trans.
Trans. I also didn't put my manganese in. There you go. All right. So make the cis. Draw me the cis. Well, that's a frightening prospect, and I don't think that I want to draw the cis isomer for this because it looks like it's going to be big and ugly, and I might get it wrong. How about you draw the waters as being cis to each other, and then just put the phosphines everywhere else? Okay. We know that the central metal is octahedral. Go ahead and put the waters cis to each other. Anywhere you want. Anywhere in the complex that you want them to be. And then put the phosphines around it. Got it?
Mm-hmm.
Where did you put your waters?
On the, yep.
This would be the sensible place to start. Okay?
Mm-hmm.
Now, can I stretch a phosphine between these two places?
Mm-hmm.
No, they're too far apart. They're trans each other. That's cis, and this is cis. So where did you put the first phosphorus?
Right there.
And then which other place was it linked to?
Go right next to it.
There you go. Done. This is the cis. So for MX4Y2, where just X's and Y's are different, we could be A's and B's, or L's and A's, whatever notation you want. That's what you get. All right, let's go one more. X3Y3. Now you can get this with monodentate ligands, or you can get this with ligands that are tridentate. Did I show you any tridentate ligands? I'm not sure I did. I think I did. I went from bidentates down to hexadentate, I think.
Mm.
I think I showed you any tridentate. There are a couple out there. Okay, if we think about this octahedral geometry being, the flat part and then 2 points up, what I can do with two types of ligands, if they're equal in number, is this. I can put an X here, and an X there, and an X here. And then a Y there, and a Y there, and a Y there. Or an X here, and an X here, and an X here. Y there, and a Y there, and a Y there. And these are not the same as each other. They are not the same as each other because the relationship from here to here to here goes around, and the Y to Y to Y goes the other way. So we see this to this to this, that's the relationship. And this to this to this. These are called, this is the Mer isomer, and Mer stands for meridional. You know what a meridian is? Have you heard the word meridian before? Have you heard? You all know what the prime meridian is? The prime meridian is a made-up line that goes through London. And we set that as being 0. Is that latitude or longitude? Longitude, right? Yeah. 0. That means time is correct in London. And then if you're to the east of it, you're ahead or behind. Depends. Depends what time it is in London, if you're ahead or behind. Is it yesterday or is it today? And then if you're this way, you're not on the same time. That's the prime meridian. That's the international line. These are in a line. The Y's line up and the X's line up. Do I have it? Well, this is a picture. I don't. That might help. Does that help a little bit? Those chlorines are really they're in the same plane.
So
if I rotate it, so if I had, do I still have an octahedron? Yes, I do. These balloons have not deflated yet. That is amazing. Unfortunately, I don't have an equal number of blues and purples.
the little one can be a purple one. Has a mark on it. Or,
This. If, oh, yeah, they don't want to take the angle. If that's a Y, and that's a Y, and this is a Y, they're in a line. Whether they're here, boop, 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 or boop, 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 they're in a line. And in this diagram, it's like, oh, I can't see it. Rotate it to you. They're all in the same plane. They're in the same meridian. And then the other one, those three make a face of the octahedral. So these are the fact. Remember, lowercase and italicized. The facial isomers, that x to x to x makes a little triangle which represents one of the faces of that octahedral geometry. These have to be, can't do this with, it's going to be very difficult for you to do that with chelating ligands. But it is achievable with 3 independent monodentate ligands. Okay, there's one more. I should call them X's. If you have a molecule that is tris bidentate, you make optical isomers. Let's pick something. Ruthenium is really famous for doing this. Ruthenium, and I think also rhenium does this. Let me see what the... Oh, yeah. I want them to be all the same. There's the one I'm looking for. There it is. This is a common undergraduate lab experiment. Let me click on that. We make, of course, it doesn't do what I want it to do. This makes a brightly colored complex ion, and the 2 isomers have slightly different Pyridine's a really nice molecule. I'm a big fan of pyridine, and its lone pair of electrons on that nitrogen is completely available for you to work with. And to make the bipyridine, this turns out to be a really good ligand. The lone pairs of electrons are really unencumbered because the ring slopes away from where that lone pair of electrons is, and just allows it to get in and do what it needs to do. Plus, it's flat. So these make, I've got to show you a 3D structure, because they make propeller-like complexes. Ruthenium trispyridine. I wonder if there's anywhere that has a rotating. Because they're flat, they're planar. What I get is this, this, and this. And so they rotate, but like complementary to each other. But if this one is pointing this way, it means that that one has to be pointing that way. Now the mirror image of this would be a rotor that is facing the other way. And they will be chiral.
Thank you.
So on the screen there is a crystal structure or a computer simulation of what that molecule is, and you can see. I think that. Oh, hello. I could have brought my iPad.
With the FD. You have that?
I have my phone. I have the that software on my phone. I'm not sure that the iPhone version of the molecular modeling software actually has a ruthenium in its set of elements, but you can see that there is a octahedral center there, and that is angled away, and so is this. And if you made the enantiomer if you made the mirror image of this, it is the enantiomer. All right, let me see if there might be. That's looking from the top down. So from the top down, it looks like that. Beautiful little ligands just occupying planes. And this is chiral. And we go with plus and the minus for what the actual deflection of plane polarized light is. I don't think we have, there's no way of doing that organic chemistry trick where you look at the central atom and you say, well, I'm going to prioritize by atomic mass all the atoms around this, and then count down. Well, it can't do that because that isn't here. So what you get, what's left is just the actual plus or minus. Did the light bend this way or did it bend that way? These are optical isomers. Okay, let's recap. There's a few other things that are there that we haven't touched yet. We just did geometric isomers. Geometric isomers give us the usual cis-trans. They now give us mer and fac if we set things up correctly. The bidentate ligands can only be cis. And there is the possibility of optical isomers. Okay, that's what we just did. There's a couple of other different types of isomerism as well. We have substitution isomerism, also known as ionization isomerism. This looks like. You take something from inside the bracket and you put it outside the bracket. I have cobalt. I have the pentamine bromide. Okay. If this is cobalt-3, and the amines are just ligands, they carry no charge with them, and the bromide is inside the bracket, then there is a 2+ on that complex ion. 3+ from the cobalt, and then the bromido is in the coordination sphere of the cobalt. Outside the bracket, there's sulfate, just being the counter ion, just being the anion that balances the positive charge. It is possible, but you won't see the sulfate do this very often, but it is possible. You see it with other halogens will jump. It is possible. Keeping that cobalt at cobalt-3 to move the sulfate in and push the bromide out. All right, that cobalt has a 3+, sulfate has a 2-. When it comes into the bracket and becomes a ligand to that central octahedral metal, that just leaves me a 1+, which is now balanced by the bromide being counter ion. So we call this stuff that is outside the bracket, we call those the counter ion. They just balance the charge. And they can be solvated and they can swim around wherever they want to be inside the flask and do whatever it is that they need to do. But they are not attached to the metal. Okay. Let's see, what else do we have? All right, there is a part where the book then gives me the option of I can go back and make another list. I can start listing the behavior of the transition metals. And give you a couple of examples, and I really do want to give you a few examples, especially around nickel, because it's so different and square planar. And I think that we need to look at hybrid orbitals as well. So we will do that. We'll do that after the break. What we'll do now is just give you a basic general second overview of what's going on in the D block. Okay. I also, at some point before we get completely off track, want to show you a tiny bit about the lower D metals and a little bit about the actinides and lanthanides, the F block, but I think that can wait much later. So we know, because we've mapped it, that the D metals have variable oxidation states. Okay. And we mapped it, so we know what's what. Let's just do some general stuff. In general, the highest oxidation states are with oxide and fluoride, the really electronegative atoms. Highest oxidation states with that. Well, we've seen that. Chromium has an oxidation state maximum at 6. Manganese, maximum at 7. That is permanganate and chromate or dichromate. We've seen those. In general, the oxides that are up to oxidation state number 4 are octahedral. Over oxidation state 4 are tetrahedral. The higher your oxidation state gets, the more covalent your behavior seems to be. And we know that the oxidation state 2, oxidation state 2 is widely available, right? But less than 2 that needs to be stabilized by a specific type of ligand. There's going to be something, it's going to be where we're moving with this class after the break. if your oxidation state is less than 2, and this is going to be a bit of a surprise, but some of these transition metals are going to have negative oxidation states. Vanadium, I did a full year of research on vanadium at oxidation state -1. That's not supposed to happen. But it can happen if you stabilize it by ligands that have something special. They have to have low electronegativity. That's only part of the trick. The trick is that they have to have empty orbitals themselves. Examples of this is going to be carbon monoxide, which we call carbonyl, which is kind of, well, we're all right, because it's a carbon to oxygen multiple bond. These having empty pi orbitals is going to reveal itself later as something called a pi acid. And if you're a pi acid, you can stabilize ridiculously low oxidation states. You can stabilize metals with oxidation states below that 2. We know metals are supposed to give away their electrons. We know that those 4s electrons are supposed to be easily lost, so the 2+ is supposed to be available. We're going to be able to see oxidation states lower than that. A lot of 0. We're going to see a lot of transition metals in oxidation state 0 surrounded by other stuff. Octahedral complexes at oxidation state 0. That's going to be normal. We'll do that after the break. Go to break.